everyone, how are we doing? It is time for office hours. We got assignment C for 320. We got soda questions. Someone said soda. I shouldn't be drinking soda, but I am. It's leftover from the wedding. So I got too much soda and my burbs are going away. Can you do some shiny help? Yeah, we can lower some shiny too. We're going to start with the soda question. We're going to do some 320. Then we'll do a little shiny. We got this all loading up. I played the intro because I'm getting the questions loaded up as we're speaking. So I'm like, okay, let me get the questions loaded up. We need the soda. My Pearson kicks you if you're not on it for long enough. It's loading in the background here. Chapter 17, the soda question on a large or a small glass. Okay. Had a little snack between 475 and 320. Well, no, 320 is coming up. What music is this? It's something like The Crows or something. The Crows? I'll tell you when I turn it off. There's a guy called That Chapter on YouTube. Does videos on bad events. He played it in one of his things. This is all YouTube copyright-free music, so I don't get hit with copyright claims. So YouTube has a whole series of things you can use. What's up, Michael? Good to see you here. Me about saying hey to everyone in the chat. Okay, so we got the question almost good to go. And this question right here, I think it's The Crows did it or something. I'll find it once I can click off of it. Okay, getting the question. Let me write down the questions people have right now. I already put the timestamps in for morning office hours. Stat 201, chapter 17. We're going to start with the soda question. Soda question. And then BS 320. Kale's wondering about question C. Asan Min 12, question C. BS 475. Shiny help. Okay, here we go. How's everyone doing today? I should speak into the microphone if you want to hear me. I know it's I'm always trying to work on the green screen, make it a little better. Top chat. Oh, thank you. Help me out with that top chat right there. Go to the main screen. We'll let the song in. It's a nice chill song. Here we go. Let's go to the main screen and work on some soda question. Okay, so the timestamp on the soda question is 3:30. Let's do this. So researchers are wondering if they give you got two glasses right here. That's what you got. Now, not like mine. We could do the route question. You got it, Brianna? Unlike what I've got right here, you got a small glass and a big glass. Now, I know these glasses are the same size, but just go with it. So you got a small glass and a big glass, and then they hand you, look, we got props today, everything here. And they give you this soda. And so you're going to be handed either a small glass or a big glass, and they say, pour yourself some soda. So you got 22 people who were handed the small glass, 24 people were handed the large glass, and then, oh, those on hand, exactly. You go back to like my waiting tables day here. That's a bad idea. But a classic three drink hold right here for waiting tables. So you walk up and you're like, you get this little, you can tell someone, you say someone hold 3 drinks nice and firm in your hand. I'm just going to pour it all over my computer and it'll be a sad day. But with that, as I hand out the drinks to the table, that's what we're doing. We're doing an experiment right here to see which glass gets more soda in it. Now, you think about this. Why is this called the 2-sample tea right here? Think about this. Why is it called the 2-sample tea? The 2-sample tea is called the 2-sample tea because there's what? Why is it called the 2-sample? That is huge. Why is it called the 2? Wow. Why is it called? Oh, it is Cinco de Mayo. Oh, I should go get that. Dang it, I'm teaching the rest. We got some margaritas. We got I'll tell Chelsea we're drinking margaritas tonight. There's 2 samples. Yeah, we do some canvas content too. Do some canvas content, you bet. There's 2 samples. And then why is it called tea? Why is it called tea? This is the tea component of it. Why is it called tea? Because Mr. T is what? And great job of Ansley and Michael right there. No, not to, I'd never do that. Dalen, no. I can't do that. UT would probably not be happy. Wouldn't be on campus, but still can't do that. This is just Coca-Cola. Nothing in it. Hey, I'm over 21, though. So Cinco de Mayo, I might celebrate. If it's online, I don't think the teacher can, but you, I don't know. You're not on campus. That's all I can say about that. And if you're of age, drink responsibly. That's all. Brian being a dad. Not literally. So it's called a T-test because it's quantitative. T-test because it's quantitative. T-test, does that make sense? Quantitative is when we're testing the mean. Quantitative, and then two means are being tested. So that's the two categories right there for the two sample T. So this question really comes down to doing the notation right here and identifying we're doing y bar 1 minus y bar 2 over square root s sub 1 squared over n sub 1 plus s sub 2. You are given this formula on the test. And this is equal to the T statistic with degrees of freedom, which we're going to have to find. That's DF. Mr. T is mean. I'm sure he's a super nice guy, but he's mean if you're doing drugs. And that's when we remember that the T distribution deals with the mean. So now we go over here and we put in the two means. It's the first mean minus the second. 4.72. I might disappear right here while we do this. So this is first mean minus second. 6.62 over square root. And if someone wants to solve this with me, that'd be awesome. 1.96, famous number in stats, but just random that we got this right here. Square it. Don't forget to square it. Second standard deviation is 2.78. Square that. Don't forget to square it. I'm talking to myself also. And we're going to find the T statistic. Now, when we do this T statistic right here, remember it is going to be negative because it's small number minus big number. So 1.96 squared divided by 22. We're going to copy that. 2.78, we're going to square that, divide by 24, and we're going to add it to the original number. We're going to square root this and get, I should know that, 0.7. Be careful, it's easy to make errors. This is 0.704. Double check your mathematics. You're going to have errors. Sometimes you do this, do it in parts, save your numbers. I've worked this a few times, but make sure you don't make an error while calculating this. Probably where a lot of the errors go while doing the T statistic. Now, all we have to do is take the difference up here at top and divide by the standard error. That's what tests are. They're a difference standardized. The T statistic is the difference standardized. So we're going to take this difference right here of 6.62. I'm doing it reverse. 4.72 minus 6.62. And we're going to subtract and divide by the standard error, which we have on the bottom, and get the T statistic of negative 2.7. That all rounds to negative 2.7. It does say 3 decimals, I think, on this one. I went ahead and found the T statistic, even though it's a little later in the problem right here, but it does ask for the T to 3 decimals. We made an error this morning on that, but there's the T to 3 decimals. Now, we have to know the null hypothesis, and we have to practice it. The null hypothesis always has the what sign mathematically. Great job, Kayla, right there, another 100 points. The null always has the what sign. Anytime we write a null, the null has the what sign. The null has the what sign. We write a null, and the null has the what sign. We know it instantaneously. The null has, and great job, Michael, there too. The null has the equal sign. And we're saying that there is, and great job, Ansley, another 100 points. The null has the equal sign, so we're saying the difference between the two means. What about the difference between the two means of the glasses? In actuality, and that's the true difference, not the sample difference. In actuality, there is what difference? Just interpret it. We're saying mu1 minus mu2, like the true difference between what people would put in those glasses. In reality, the null assumes that what? Once we put this equal sign right here. Like, talk to me like just normal. Like, be like, well, what we're seeing right here, we're assuming that there's what? What does that read? Mu1 minus mu2, which is the true mean amount of soda put in glass 1 minus the true mean amount of soda put in glass 2. We're talking about the difference. We're assuming what? Which they kind of get it right here. The null assumes. This is good for your project, too, because it kind of breaks it down into words, what we're talking about. We assume there's no difference. Great job right there, Kayla, right there. We assume there's really no difference. So they're the same. Like, you could mathematically just put this mu over to the other side. We're assuming there is no difference between them, that there's no difference as far as we can tell. Now, the alternative right here, they're asking, people are randomly given, I think it's a two-sided. Research to investigate how the size of a drinking glass affects how much soda people pour for themselves. It doesn't indicate people pour more in the large glass. What it indicates is we're looking to see if there's evidence of a difference right here. So difference would be that they're not equal. Is the alternative is going to be, great job, Fleming, right there. I saw the nod last second. It's going to be not equal to. And that would be that there's a different amount, different from, like, these means are different from each other. We're not indicating a sidedness. Now, why is that sidedness so important? Why is it so important we figure out if we're doing like a greater than, less than, or not equal to? Why is it so important that we figure out, are we doing a greater than? Are we doing a less than? Are we doing a not equal to? Because the greater than, the less than, or the not equal to goes to the way we do the what. The way we what the curve. Because we're going to take our T statistic, and here's our T statistic. Oh, really? Here's our T statistic. Oh, I hate that about this app. It's going to determine which way we shade it, right? Whether we shade SAP, it doesn't let you add in more decimals. I need to talk to the person who made this. So if we do the left tail, it looks like this. If we do the right tail, it looks like that. Why is it making it positive? Oh, I put in degrees of freedom. No wonder. We'll just put in 55 for a second. If we do the right tail, it does this. The left tail, it does this. And the two tail, it does both sides. So you can see how it works, and it goes to the way we shade the curve. So the way we shade the curve is based on doing a less than test, shading to the left, a greater than test, shading to the right, and a does not equals test shades both sides. A little bit interesting how this is solving right now. Oh, man. Just wanted to show this. If you do the less than test, that's 0.05 or 0.5%. The two-tailed test is double the smallest. Look at how it doubles right here because you're just reflecting it on the other side. And then the greater than test is going to be above it. So those would add up to 1. Important things, there are test questions that do that don't show you all the p-values, and then you have to know that the less than, the greater than add up to 1, and the two-tailed is double the smallest. We've done a few reviewing that. So now that we understand how the p-values work and why it's important that we chose that this is a two-tailed test, we need to enter in the degrees of freedom. The degrees of freedom tell you which t you are using. So we need to put in the degrees of freedom applet right here. We've still got the picture up. Good stuff. 2 seconds right here. The degrees of freedom applet is appearing on the screen. And I'm going to take this information and let's see if we can get it on the screen at the same time as it. And you will see how you'll take this information. Now, the 2 sample t degrees of freedom is a too complicated formula. Really? We just say it's too complicated because we do not solve it. We're going to put the sample sizes in here of 22 and 24 respectively. The standard deviations of 1.96, the standard deviation 1, sample size 1, and the standard deviation right here. You would not solve this by hand. If you are watching in the future, we keep saying that the 2 sample t is a too complicated formula. What do we mean by that when we say it's too complicated? Well, 2 sample t degrees of freedom, the formula, I'll show you a picture of it. We say it's too complicated because we don't solve it. Copy image as. Here is the formula right here. This is the formula you will never solve for on the test. And sometimes test questions have, it's wizardry. We're not going to solve this. This is what that applet's doing. We're not doing this math right here. We're not doing that whole to find the degrees of freedom. What is, who knows in the chat now for 500 points, what are the degrees of freedom for a 1 sample t, which is not the test we're doing, but this is a review. The degrees of freedom for a 1 sample t is a very simple formula. 1 sample t is what? So these are things you want to put on note cards if you're watching this right now. 1 sample t, n minus 1. Great job, Kayla, right there, all that review. Yeah, you could just, well, that's what this is doing basically for us. It's just solving. A great job, Michael, too. 1 sample t is n minus 1. And then we say that the 2 sample t is a too complicated formula. If you hear the alliteration right there, the 1 sample t is n minus 1, and the 2 sample t is a too complicated formula. Like we're not going to solve it. So we use this applet right here to get the answer, and then you take the degrees of freedom and you bring it over here. We need to take our better z-score and do 2.96. So there is the p-value, 0.01. And does it want it to 4 decimals? I might use R to check the answer. If I get this wrong, I'm going to be really sad. It says 4 decimals. Okay, we know for certain what our conclusion is going to be. We can't get one wrong. We lost the streak earlier today, and we lost it because we didn't enter enough decimals on the... We rounded this one up top, and we got an error there last time. So the decision on this test should be very clear, though. Look at your alpha level. Yeah, it should be. If you get this one wrong because of, let me know. But make sure you're not using the normal applet. If you use the normal applet, you could get it wrong. The normal applet comes to very different answers. If you're like decimals off in the 10,000ths, we'll fix it. I might use R to check it in a moment. Look at your p-value and look at alpha. How do we know to reject the null? This is good practice right here on how do we know to reject the null. So when do you reject the null hypothesis? Do I reject the null here, and why or why not? So we see the alpha, and we look at our p-value, and we ask, is p-value what to alpha? So it's above alpha, and so Michael, keep going. What decision do you make, alpha? You are right, the p-value is above alpha, so what decision do you make, Michael? Keep going, great work, 100 points right there. What decision do you make? You have correctly identified that the p-value is above alpha, alpha being the level of significance, usually assume 0.05. If the p-value is high, you just let it fly. You do not reject. So we do not reject, which is the same thing as fail to reject. And if you do not reject, you do not have evidence for the alternative, which means we're investigating if they were different. We're going to do a quick check right here because I'm a little scared. So we're going over here to QT. And we want first the degrees of freedom second. I'm cheating. I'm using R. And I'm going to see if it gets it right either which way. There's the 1 NAs. What did I do wrong on my QT? Or is it PT? I always get PT and QT pure. Okay, it's that times 2 for the two-tailed. So here's the very exact, Kayla. If we are off, it's because this is the super exact. 0.01. Wait. Can Brian not read? Does everyone see it? We were super off because my brain is not on. It's not 0.10. Ooh. It's not 0.1. What was I saying? I said 0.10. It is below. Fleming right there. Fleming getting everyone 1,000 points. Big error on Brian's part. I thought we were looking at, I was speaking of it like this, saying it was 10, but it's 1. That is p-value low, reject the null. That does provide evidence. So great job right there, Fleming. No, I'm not. So great job right there, Fleming. Good catch before we turned in this question. I'm glad I went over to R for a second. I was like, wait a minute, that's 1%, 1.01. A more exact calculation on the p-value. We should be fine. Don't you do it. Don't you do it. That's what I like to see right there. So this is the more exact calculation right there. It's got a little bit of a leeway. Would it given us this? Oh, you see, there's where it's wrong. It would also give us this right here. So it's got some leeway. I wonder how much of a give it has on the right answer. There's some on the thousandths, which is nice enough. If you notice, it's got a little bit. I want to see what it's plus or minus. So it goes up to that. And that means it has to go down to... There's right. And then it should include this one. And then, okay, so it is centered on... That's interesting. It is centered on the exact answer I got from R. Plus or minus 3. The answer is plus or minus. So I could do this. Add to it the interval of... This is the range of values you can give. There's the range of values you can give. And then we could round it to 3 decimals. So this is why I love R. Doing a little bit of R. Here, we're going to do more questions here in a second. Round to 4 decimals there. Oh, what? Oh, I'm doing digits. Option digits equals 7. There we go. That's the range of values you can give around the perfect answer. So that's why 0.01 was in there. 0.01 was in there. Good stuff and good catch. Let's continue on. Can you do the problem 3 on the homework, the one about the man who moves to a new city? Jackson, we can. We did last, and we'll do it here too. You got it. Happy Cinco de Mayo, everyone. Woo! Time for some more questions. That's a good one right there. Make sure to look at your p-value. See if it's below alpha to reject the null. Remember, p-value low, reject the null. The song was... Dylan, I'm going to tell you the name of that song. Someone's wondering the name of the song. The song is The Crows Did It by Nathan Moore. The Crows Did It by Nathan Moore. Okay, the next thing on the list, let me get Man Moves to New City. We'll do that here in a little bit. We've got 320 next. Chapter 17. Bike Route, New City. Okay, Man Moves New City coming up here in a little bit. We're going to do a little 320 right now. Model building. Kayla's wondering about question C, I think. Okay. Okay, let's do some question C. Here we go. And the time is 20:44. With this right here, have to check out the channel that was to it. Oh, wait, which one? Yeah. So we're going to scroll down to C. Do we have a mark for C? There's C2. There's C1. You can go through the bookmarks right here. Are you speaking of this one right here? Interactions may be important to incorporate in the model, but running reg subsets with interactions would take too much time. Instead, we will run the step search on a model. In step, let's see direction both so that the procedure is free to add or remove terms from the model as needed. Remember that the full model in this case includes all two-way interactions, which would be the y variable tilde dot, meaning all x's raised to the second to include the interactions. I suggest having trace 1 when running it so you see it, but turn trace 0 when you knit. Good stuff. Okay. So we need to talk a little bit about the step procedure here and what is a step procedure. It always helps to just kind of make sense. You know I love talking about food. Okay, Brian is going to travel from Texas and he's going to go up to New York and he's going to find the best pizza. Pizza time. Who's with me on this? That Brian's going to go from Texas to New York and he's going to try to find the... Sure, let's do that. He's going to go from Texas to New York and try to find the best pizza. He's searching, trying to find the best pizza. Does that make sense? Like, I'm going to go searching for the best pizza. Now, with this, what ways can I go towards New York? I'll give you one answer. Brian can go forward towards New York. There's one answer. Brian can go forwards towards New York, or he could do what? Just think he could go forwards. Like, he can travel this pathway forwards. He can go... There's Brian traveling towards New York. Or he could do what? Think of another... He can go forward towards New York. Or what else could he do? Well, we're not going to detour to Canada yet. I can drive towards New York. Just be like... Well, I can go forward. So here's the key word. I can go forwards, in other words, towards New York. Or I could do what? What are my kind of options? I'm either going forwards towards New York or what? You can think about it. I'm either going to New York, like I'm either going towards New York, or I am going away from New York, right? So we could say, go home to feed Morty. So we got here forward, or I could go maybe backwards. Does that make sense? So that makes sense. That's horrible writing right there, but that's backwards. We go forwards or backwards. Are you following me on this analogy so far? We can go forwards towards New York or backwards towards New York. Because maybe if I'm traveling this pathway, maybe I realize right here I need to take a detour and go back this way and go backwards. Does that make sense? And maybe I'm like, oh my God, we need to go backwards a little bit. We need to go away from New York and go back this way. So what are we talking about right here? What's the analogy? What is the starting point for creating models, Kayla? What is the starting point when we create models? If we want to start from a baseline with nothing at all, we'd start with the what? We'd start with the what? Start with a baseline. Well, we're going to pick our x's like descriptive modeling. Well, so if you start with a model that's like the simplest possible model, let me rephrase the question. Start with the simplest possible model before you even pick x's. That's a hint right there. The simplest possible model that is little information as possible, as simple as can be, rather something about the world. Rather what? A rather what model? We talk about it in time series too. You'll both know it as a model that looks like that. But one of you will have different ways of using it. The naive. So the naive down here has nothing in it. Over here, we have a model with all the variables, called the full model sometimes. So the full model has all x's. Does that make sense? This is all your x's. So what do you think we're doing as we're going forwards right here? As you go forwards towards the full model, you would be doing what with your model? As you go forwards, you'd be doing what? You'd be, as you start from a model with no x's, we're adding x's. You're figuring out what x's to put in, like descriptive modeling, right? You got to figure out the x's, give them coefficients, and interpret. So we're going to start here with the naive model and then start putting in things. But if we go backwards, we'd be doing what? We'd be going towards the naive, right? So if you go backwards, this is called backwards step, where you procedurally, because you could technically start right here and move backwards on a backwards selection. You can start anywhere on this process. You're taking them out. You're removing them. But what if I said there's such a thing called both, or mixed method? If we allow for it to go both, then one with that allows both is when you can do what? Both allows for the what? If you allow for a mixed or both stepwise model, you can do what as you put things, or what? If you allow for your selection of variables to be both or mixed method of selection, you can do what? You can add or remove x's at any point. So as it does the model selection, if you do forward, you can only move forwards. If you do backwards, you can only take out things. If you do both, you can add things and remove things from the model, depending on how valuable they are. Now the question becomes, how do we know what to add and remove? What we'd be doing here, and I'll show you how this works, is we need to first make a naive model. We need to make a full model. Okay, so data, we're going to use our example data right here, survey 10, and we're going to take the variable of interest as height. And the height is going to be explained by tilde dot squared to second. It's all the variables. Data equals survey 10. So there's the naive model, and the full model is going to be virtually identical, which is going to copy paste this full model right here. Oh, that's not the naive. That's the naive. There's the full model. Okay. So now we got the naive and the full. The naive is tilde 1. It just creates an intercept, where the full model is tilde dot second, and we're including interactions, hence raised to the second. The dot means all the variables. The raised to second means we're including interactions, and the 1 is just the intercept for y tilde x. And so with this right here, got to remember the step procedure. The starting point is we're starting with the naive model right here, and then we need to do scope equals list lower equals naive. And we're going to make this look pretty today. Let me stay inside of here. Upper equals full. Trace equals 1. And it might make more sense, instead of saying trace equals 1, if I instead say trace equals true. True and 1 are synonymous and they're binary. Now, what this is going to do is it's going to start with which model, Kayla. I'll highlight things as I talk about them, so if you need a cheat, look over here. I have decided to start with the what model right now. I have decided to start my search procedure with the what model. Oh, let me go direction. I've decided to start with the naive model. So we're starting with nothing in it. And then I've created fences. A lower fence is saying you cannot go below this. An upper fence says you cannot go beyond this. Oh no. So does this make sense why I have this scope of models that I will consider? Says you cannot go lower than the naive, which you just can't go, and you can't go beyond the full model. So you can go up to this limits I'm putting and say you can take out up to the naive, you can add in up to this. And then this says we can see what's happening, and this says you can only move forwards. So watch this. There. Did you see it? It's actually a lot. This is what ran in the background. All of this. That's what ran in the blink of an eye. Like, watch it again. Done. It just searched hundreds of models. Maybe up to about 1,000. Let's look at what it does, though. Let's go to the very start of this. Let me rerun it and show you the very start. Third time running it. When it does this, what model do we have currently? What model do we have currently? Oh, and the trace means we get to see the output. Trace means I get to see the... If I put trace 0, you don't see what happens. Right here, do we have... Good job, Sophia. We have the naive, right? That's the naive. And what are we evaluating about it? How close it is to the what? And we're trying to figure out... We're trying to predict someone's height right here. So what is that? What is AIC, which is where we ended last class? What is AIC? You can tell me the name of the Japanese statistician. You can tell me what it means and what we like about it. What is that? AIC is the Ake-Ike information criteria, famous Japanese statistician, and it means how close we are to the truth. Good, don't worry, Kayla, I'll keep going on. Thank you, Kayla, so much for the... Yeah, of course. Of course, you're always welcome to, Kaya. And you're hearing a little bit of it now. Kayla was in your boat last semester, and she's rocking, doing great at 320. So we want it to be low because remember, it's closeness to truth. So you want it to be as low as possible. You want R squared adjusted to be high. AIC you want to be low. And Dylan knows some AICC from 475, the Ake adjusted criteria, AICC. So it's just a corrected one. Why do we use AICC? AICC has an additional penalty term on it. It's just a harsher, it makes it harder to get more complex models. They're both technically fine. Like, it's like tomato. They're both very similar. We want it to be as low as possible. AICC you want to be, or AIC you want to be as low as possible. Ake just came forward and made more adjustments to it and made the Ake corrected criteria when he made it even better. If you looked at this right here and just look at the AICs, which variable would you choose to put in here? And this model's nice and neat, playing golf. Which of these would you pick to choose? And that's the reduction in sums of squares, Which of these would you pick to choose to put in the model? You can pick, I'll let you pick one of these. Which one would you pick? Lillian, you're right? And guess which way this output's organized? So when you see what happens right here, guess what the model did? You don't have the naive model anymore. Guess what you have? It did what? It put that where? You don't have the naive model anymore. It said, okay, this is the best. And it said, okay. It put it in the model. Do you have any idea what will go in the model next? We're trying to predict someone's height. And the best thing to predict someone's height is someone's desired weight. Like if you say to someone, how much do you want to weigh? And someone's like 170, you probably have a pretty good guess at their height at that point. So what do you think the model's going to do next? It added that X, right? So just think about how this output looks and imagine when I scroll down what it's going to show. Because it's evaluating all of these on the AIC to say, it's going to put gender. It's going to say, well, gender reduces the AIC the most, and then it puts that in the model. And every time you put something in the model, it has to reevaluate. Does that make sense? Like each time you put something in the model, it reevaluates. So it's going to then put weight, and then it's going to put the interaction between weight and desired weight. Then it's going to put the number of body piercings. Then it's going to put weekly video games. Then it's going to put gender and weight interaction. Then it's going to put gender weight interaction right here. And it's going to keep doing this. And it's doing tons and tons and tons and tons of things of doing this till finally you get to right here. And what do you think this choice is? What do you think it's after it puts in all these variables and it's got an AIC right now of 1327? What do you think this choice is? It says none. And oh, the AIC might have wrapped around the screen at that point. Here, we'll expand this and we'll redo it because I want to see the AIC. Oh, what? Click the button. Right here. So the AIC is currently 1327.7. Well, now, here's the top choice. Do you notice something? What about if we were to add this variable, the AIC would do what? Yep. And if we were to add this variable right here, Kayla, the AIC would do what? Look at the AIC now. And if we added this variable, the AIC would actually do what? Hence why I don't think we should add that. Because if you add this variable, the AIC will actually increase. Because it always puts them in order right here. So the choice of doing nothing keeps the AIC the same. You see, that choice is always here. It's just usually not at the top of the list. Like there's the choice to do nothing. All of these right here lower the AIC. So the algorithm ends on trying out variables when there's not a variable to help it. So if you want to go really crazy though, notice how these all have pluses. Why does every single one of these have a plus on them? So I want you to look at my code and think, why does every single one of these have a plus? And think to our analogy of driving towards New York. Why does every single one of those have a plus? And the answer's in the code. Why does everything with this step procedure have a plus on it? Theoretically, you could put everything in. You would just say, this is good, this is good, this is good, this is good, and yeah. Well, so the reason everything has a plus is because we're driving towards the full model at all points because I'm doing a what selection procedure. At all points, I'm driving towards New York because I'm doing a what selection procedure. Up there in the code. I'm driving towards New York because I'm doing a what? I'm adding things in, and this is called what selection of your x's. It's on, so you're right, I'm adding things in, that's over there. So I'm adding things in. That's known as what selection of the X's. Forward selection. Great job, Lillian, right there. Now, I want you to... These are questions we put on the final. You ready? We're doing a little bit of final review right here. So I want you to think about this. What model am I currently at? I think it's backwards. I might have spelled it wrong. I'm currently at the naive, right? What happens if I go backwards from the naive? I think it's backwards. Not backward. Forward. Might be backward. I think it's backward. We'll find out when I run it. If I'm at the naive, yeah, teaching to the final moment. So if I'm at the naive, backward is going to do what to X's right here? Well, be careful. We're at the naive and we're going backwards. So this is weird. Something sounds odd, right? I'm at the naive. So here's what it looks like, Kayla. You're at the naive. So you're currently at the naive, and I'm saying go backwards. Well, you could do that, Lillian. That is correct. Lillian, that is correct. We'll do that here in a second. But if I'm at the naive and I go backwards, because I think I've written a test question like this, what happens? So we have no X's, and we're going to try to take out X's. That's what I'm saying. There's no X's in the model, and we're going to try to take out X's. So what's going to happen here? If you have no X's and you try to take out X's, not negative, just nothing. That's the code. Because we have no X's. And does that make sense? So what model did it finish off telling us to use right here? We said start at the naive and try to remove stuff. So what did we... Not really an error, just... It said, hey, use the naive model. You start at the naive and you try to remove stuff. Well, there's nothing to remove, so you got the naive... That's the naive model right there. Does that make sense, like, theoretically? We said start at the naive and remove things. And it said, well, there's nothing to remove. Here you go. Here's your naive model. Now, Lillian pointed out excellently, Lillian, that's worth some 500 points. We're going to be doing some more 201 here in a second. Lillian, 500 points, because Lillian said, don't start at the naive if you want to remove stuff. Start at the where. So repeat it again, Lillian or Kayla, either one. If you want to remove things, you shouldn't start at the naive with nothing in it. You should start with the where. If you want to go backwards, you actually need some X's in your model. Technically, you can start anywhere, probably as long as there's X's in the model. You could take the full model, and this is where you're starting. That is the starting point we are using. So let's put things in our model, and then let's remove things and take a look. Oh, this is where it's going to be crazy. It is considering removing an insane amount of stuff, and it's rather fun to watch this. Now, you might say this is taking a long time. I'm trying to remember which office hours it was I crashed my computer making all possible models. If you make all possible models, you will crash your computer with this one. This is quintillions of models, if you look at all possible. This is considering maybe thousands or tens of thousands of models right now. So it's really rather cool to think you're making thousands of models right now. Tens of thousands of models. Yeah, we've seen some stuff with 475, 474. Oh, well, yeah, time series cross-validation. You're like, I've done time series cross-validation. This is not that long. I can still see this is running. So time series cross-validation, this will keep blinking faster and faster and faster. It'll start to get to where it just takes off like a rocket and usually finishes, as long as it's removing things. Oh, we did do backwards, so it is constantly going to remove things. We'll give it another minute or two. But you don't have to just go backwards. I'm pretty sure the argument is both. If you want to go backwards and forwards, you could take things out and remove things. At that point, you could start at the naive or the full.
It doesn't matter.
I mean, it does. You'll go to different points. So you would say, why do we have backwards selection? Why do we have forward selection? Yeah, no, this is rather fun, rather interesting, and these are advanced search procedure algorithms that are pretty cool to look at and pretty fun to like see what you get model wise. Since we're storing it into S, you can then do a summary of this and look at what you have. So the model will be stored into S. Does that make sense, Kayla? We'll be talking about this today and reviewing it, and I guess we might do the retreat tomorrow. It's so busy. Only have a few more days. Come on, code. You got this. Blink, 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 blink. Just takes off like a rocket here eventually. See, it's going faster and faster. It's got less models to evaluate. We're gonna do the new route. Then we got some new questions. Put those questions. Yeah, it's starting to take off. Then it'll like slow down sometimes. And this is a very good computer. Let's see what our final model is. Our best model at predicting how tall someone is. We're about to see here shortly. The best model we have for I told you. I've done this a few times if you can't tell. There it is. Here's our best model, Kayla. The best model at predicting how tall someone is the following ridiculous model that predicts 75% of the variation. R-squared adjusted, not so awesome. Everything is awesome except for the R-squared adjusted. And wow, that is a very complex model. Pretty crazy. A lot of significant things in here. Like desired weight is interacting with so many things. So is weight. This is a super ridiculously complex model. Very hard to interpret. But yeah. I guess when is it due, Kayla? When is the activity due? Head over to the main screen here. When is the activity due? Let's play a new song we don't usually play. I like this one. We don't hear it so much. It still has a lot of things. Yeah, it's got a ridiculous model. That is insanity. When is the activity due? Someone moves to a new city. Moving to a new city. Need to find a good house in Knoxville. Move to Knoxville. Tomorrow? Oh, yeah. I guess we might need to do it. Maybe we'll do it at the end of class again. Didn't we do that last week? Yeah, maybe we'll finish class early and do it at the end of class. And we'll review on the final day. I think that helped people out, but we had to end the stream, right? Did we do that last class? You ever have where things just blur together? You're like, what day is it? Who am I? Hopefully that's not you. Hopefully it's not me. Yeah, we had more people doing it, right? So we should probably just do that. Probably the best way. We had more people interacting, so I think you might be right. That might be our goal right there. We might do that again. Might be sneaky. Maybe the class before. Yeah, I think it was last Thursday. So I think that's probably what we're gonna do. We're gonna get it done. So probably be responding to stuff pretty later tonight. I've been in college 7 years. Almost all of college is just a blur. If you have time, you can go over AIC again. Yeah, what are you wondering about? We can do that here in a little bit. And Dylan, if you have questions, Dalen. If you have questions about the shiny, let me know. What were you wondering about AIC? The main things to know about AIC is the smaller it is, the closer we are to the truth. And an AIC difference of 2 is very small. AIC difference of 10 is a little bit larger than we would like. And we use it to compare models. So AIC is a metric to do model comparison. And the smaller the AIC, the better, i.e. the closer it is to the truth. Do you have a shiny question? Yeah. We don't interpret it. It's just lower is better. It's just like you get your report. Here's the AIC. You could use it to compare to another model. So if you have a model with an AIC of 10 and an AIC of -50, which model would you pick? Just on that information alone. One has an AIC of 10. One has an AIC of -50. Which of those would you pick? So it's just used to compare models. There's not really any... my AIC tells me this. It's just like, we don't really interpret it. It's just a model comparison metric. It's like, okay, that one's 10, that one's -50. I'm going with the which. You can do, there's a function AIC, capital, I think it should be just AIC. We're gonna start the two-city problem here in a second. I believe if you do this right here, let me double check. Oh, I don't have a model stored into it. That's why. Yeah. Just run AIC of your model or step procedure, and it'll do it right there. Oh, Kale's got some good stuff right there. Let's check out the two. Oh, thank you. When did I do? Is that me? Or is that? Thank you. Wow. Whew. Here we go, everyone. Thank you, everyone, for all the views and all the interactions. Pretty crazy, like how many things, just crazy amounts of someone put a nice comment on our channel today. Okay. No worries, Lillian. We're gonna put on our music and Brian's gonna get that energy. Here we go. Two cities problem. Do some shiny afterwards. Let's do the two cities problem a little bit slower this time. Here we go. So the two cities problem. Now, when it comes to the two cities problem, this is a notation problem. This is a notation problem. With a notation problem, make sure you can identify each part of the problem. We're going to go more slowly. We did a speed run of it last office hours, but this is the more slow version of solving it. So let's take a look. You have moved to a new city, and you've got the option to use bike route A or bike route B. So here's the bike route A, and here's the bike route B. So when you look at this, it's hard to tell just even visually which one's faster. But remember, bike routes are not all created equal because maybe you never know what stoplights you're going to hit or what's going on. But you're like, I'd really like the best bike route. So you look here, and with bike route B, what do you got? Here, we'll do some highlighting. Bike route B, which is this one right here, on average takes 53 minutes. Ooh, with a standard deviation, that's the variation, is 1 minute. Now, you've biked this route 20 total days, which is also the amount you've biked route A. So A and B were both biked 20 days. A, though, bike route A took you 48 minutes, and it had a standard deviation, which is the variation of 3 minutes. Now, let's pause here, and let's just do normal things like we would. Bike route B was taking you 53 minutes on average. That's ridiculous. Was taking you 53 minutes. Bike route A is taking you 48 minutes. What is the difference between how long these bike routes take you? Just think of this. Don't think too much about the problem yet. So it took on average 53 minutes for bike route B, took on average 48 minutes. Just think about you just 53 minutes on average on this bike route, 48 minutes on average on this bike route. So what is the difference? Like, if you're looking at this difference, you'd say, oh, on average, the difference is what? Like, we're looking at, like you biked each 20 times, took an average of 53 for one, took an average of 48 for another. What is the difference between these? 5 minutes, Michael, right there, 100 points. You're right, 5-minute difference. All my pens hate me today. Five minutes. So the question becomes, well, maybe there's not really a difference. Maybe the difference is, variation. What if I told you the difference was 2 seconds? You'd be like, well, they're probably about the same, right? If I told you the difference was 30 seconds, you'd say, probably still about the same. If I told you it was 2-hour difference, you'd say, well, of course one is faster. Statistics looks at this gray zone to be like, is 5 minutes really a big difference? Like, what do we think the difference is? And to do this, we're going to have to make a what to estimate the true difference. We're going to have to make a what to estimate the true difference. I'll start writing it out right here while you consider what we have. So the problem does it B minus A, but here's the difference we observed in the sample. And so now we need to make a what, and that's the key thing right there, for the true difference. Because we saw a difference of 5 minutes, but I don't know, what's the real difference? Like if we think about, in actuality, I take 5 minutes, yeah, maybe, and we're not even considering those Y objectives. So we need to make a what for the true difference right here, because we see what the sample difference is. In our sample, it was 5 minutes, but we're trying to figure out what the truth is, like in actuality, how much longer or shorter these bike routes are. So we need to make a what, and we're talking about this thing right here. That is the equation of a what. Because here's what we observe in our sample, i.e. this number right here of 5. Technically, this is going to be, it is 5, because it's 53 minus 48. We'll start plugging in the numbers while you think what we have right here. Now we're going to get stuck on one of these, and I'll show how to get it. Remember, Route B took 53 minutes on average. Route A took 48 minutes. That's the sample difference observed. And then we need to make this little thing here. This is the important part. This is the margin of error of the what highlighted right there. This is the margin of error. We'll find this quantity right here in just a moment. That's the T statistic. More on it in a moment. We biked each route 20 times. The first standard deviation was 1 minute squared plus 3 minutes squared over 20. And so this is a confidence interval. A confidence interval always has with it a what? Confidence intervals always have a margin of error, which is everything after the plus or minus. And then they also have a center, which is the estimate. So this is the center of the interval, which is your estimate of the truth. And this is the margin of error right here, which also contains our confidence level based on the T. So usually the T statistic is the tougher part of this one because we have to go to a T applet to get the degrees of freedom. And then we have to go to another T applet to get, and I wish we should just make one applet that does it all for you. But this is the cumbersome part of of this assignment right here, where we have to go to the T applet right here and put in, we can show them both on the screen. We have a sample size of each route of 20. The standard deviation of the first is 1, and standard deviation of the second is 3, and you get degrees of freedom 23.17. Next, we go to the T applet right here, and we need to put in the degrees of freedom we just found. So make sure you get these degrees of freedom by putting in the numbers respectively. Look how we have the notation right here. Sample size 1, sample size 2. Standard deviation 1, standard deviation 2. And that gives the degrees of freedom, which tell you what shape of T you're using. Notice how the shape changes. So the T changes shape as you do this right here. Put in your degrees of freedom right there, and then ask what kind of confidence interval you're building. Pretty sure this problem is usually a 95%, and I'm going to make sure I keep my degrees of freedom right here as I go to 95% contained within the interval. This means I'm going to use a T of 2.069. This is the correct degrees of freedom, 95% contained in the middle. It has the between right here. So we are going to use 2.069. The plus or minus is included in this because we are doing the between. I prefer to do it this way, and it looks like an interval, 2.069. That is the T statistic. That's pretty much one of the harder parts of this problem, 2.069, because you have to do a little bit of work to get it. There we go. One last try. There we go, perfect. Okay. The margin of error is going to be the standard error. The standard error is going to be this right here. 1 squared is 1, 3 squared is 9, 9 and 1 is 10, 10 over 20 is 1/2. 1/2 is 0.71. So let's do 1 divided by 2, square root. And it's 0.71. Very close to that. Then we're going to times that by 2.069, and we've now found the margin of error. I believe this question has us rounding to 2 decimals, so 1.64. That is the margin of error. Be careful on your mathematics, but the margin of error right here is 1.64, which is the plus or minus. And the estimate of the interval, as we said previously, is 5 minutes. It's just those numbers subtracted, plus or minus. And then the margin of error is 1.64, we said. 1.64. 1.46. Pretty sure I didn't make a mistake on that, did I? Let's double check. Don't want to get it wrong. Yeah, it is, because it was 0.7 something at times 2. Got it. 1.64 is the margin of error. Oh my God. Yeah. Yeah, no worries. Great work right there. Yeah. It's a tough question. Great work, Jackson. 1.646. Thank you, Michael, also. I'm glad this can help people, because that's my goal, is like to help you understand what you're doing, the point of this. So we go 5 minus margin of error. Really? 5 minus 5 minus the margin of error, 3.45. And then 5 plus the margin of error, 6.46. Someone says 5 minutes. Well, that's literally the center of the interval. Yes, it's the literal center of the interval, because my interval contains a check answer. Woo! So it's a longer work question. We did this one during the other office hours too, but we did a speed run of it. So this is a better solve of it, more in depth, more of a talk through of it. Please do a walk through the theory of it also, like what are we doing? Why are we doing this? We're comparing here 2 means. We're comparing the mean time of route A versus the mean time of route B, and we're trying to investigate, is there really a difference? So this interval down here, or the one we made on the problem, is our interval to estimate the true difference. So be careful here. Yes or no, do we think there is really a difference between the routes? So I'm not asking what they're asking. I want to know, do you think there is really a difference? We're not talking about the old timers claim here. Do you think there is really a difference? And try interpreting the interval to basically know what you're doing right here. You would say, I am 95% confident the true difference between the mean time of route B to mean time of route A is contained in the interval 3.54 minutes to 6.46 minutes. Now, the interval is completely positive. And since the interval, and so to their question, 5 minutes is believable. That's their last question. So we're kind of going beyond this. Jackson, great job right there. That is the answer to the question they've asked. But I'm asking, do you think there really is a difference? Now, I'm not trying to trick you, so don't think, oh, he's going to the reverse right here. So I'm kind of saying the answer is yes. But why do you think there really is a difference? Because when you look at the interval, so don't look at their question, why do you think looking at that interval, that the interval would imply there really is a difference between the route times? Because you're saying, like, what is the difference between the route times? And you think it's somewhere between 3.54 minutes to 6.46 minutes. And notice how 5's at the center. because the one route, exactly, Michael, that's exactly it. And this is like a beyond the question we're doing, because you're right, Michael, that 0 is not contained in the interval. There looks to be a difference. It looks like route B would save somewhere between about 3.5 to 6.5 minutes. Does that make sense? If I'm going to talk to someone normally, I'd say, yeah, it looks like route B is about 3.5 to 6.5 minutes faster. Like, I'm pretty confident of that. Like, I bring in the mathematics, and it looks like sounds like it's easy. Yeah, we do a lot of like a 0 contained in the interval, because that's how the output looks when you do the 2 sample T. We did some earlier. You can see right here 0 is not contained in this interval. So on the 2 sample, you reject it. So that goes to like 0 is not contained in this interval. The two-sided test rejects. I said 2 sample, but it's 2 sample because of that. So understanding what the output looks like and understanding how to connect these ideas, whether you're looking at the output or the test, know how to get the T. It's the different standardized. Can anyone tell me very quickly, 1,000 points right here. I'll take it to 1. You don't even got to throw a decimal on it. Just tell me what's the margin of error of this interval on the screen. Should be able to very quickly get the margin of error like that. Does anyone know the margin of error of this interval? Super quick. If you know the margin of error, you're really good on this. You can do it to just no decimals. It's basically this. You could round everything and basically say it really easily. So just think about what margin of error is. Look at that. Sometimes we blank out margin of error stuff. Can we and confirm we still? Yeah, it's still, yeah. Oh, looking for zeros is super important. Like, is 0 believable? 470 wants to. Close, Michael, close. I see what you've done, Michael. So think about, you just said 8, but it's not 8. Because this is the center of the interval. It's not 8, Michael. I'm trying to give you a hint. It's not 8. You said 8, but it's not 8. It's not close to 8. Common mistake. And I love asking questions for this reason. It's not 8. I know where you're saying that. It's not 8. 4. Great job right there, because in always the common error is to not to divide by 2. Does that make sense, Michael? Great work right there, Michael. If you want to figure out exactly what the margin of error is, you go half the length of the interval. So you can kind of look at it and be like 39, 31. That's distance of 8, half the length. Or you could go exact. Using it more exact. I mean, it's basically 4. Basically. You could also go from the center up. Yeah, of course, Maria, anytime. There's right there. Mm-hmm. You can call him Ubot too. He answers everybody. So if you call him Ubot, you doing all right, man?
Notation, brother.
Ah! I hit all the wrong buttons.
I am Ubot.
There he is. In the chat, he's everywhere. Brian's got to memorize his buttons. What questions are there? We doing a little shiny? What are we going to do? Adult and children's cereal? You got it, Jackson. Here we go. Let's go back to the main screen. Okay. Mubot, you doing cool?
I am Mubot.
He's mad today. He's always mad, Mubot. You chill out, Mubot. You chill out. Do a slower version of adult versus children's cereal. Adult versus children's cereal. Oh, what's that? Cinnamon Toast Crunch. I am a product of the 90s. My burbs can't handle. That's not green. That's yellow. How's my burbs not handling this? Stat 201, chapter 17. Cereal question. I misspelled it earlier. Boop. How do you spell cereal? Yep, that is correct. Okay. Timestamp incoming. Let's do it. Raisin Bran is peak. Raisin Bran's not bad. Raisin Bran's pretty all right. I prefer some Frosted Flakes. Give me some Frosted Flakes. Or some Captain Crunch and just cut open the roof of your mouth. Reese's Puffs. Ooh, or Rice Krispie Treat cereal. Could you help me with interpreting the true proportion of my diet? Yeah, I'll take a look, Jonathan. Yep, drop it in the... We can do some interpreting. You want to do the true proportion? We'll do that here next. You got it. So we have here data. You're going to go in, pour yourself a nice big ball of Reese's Puffs. Now, when I say Reese's Puffs, am I talking about a kid cereal or adult cereal? You've got to imagine this problem. You got to use all that imagination. And the rainbow turns black. Am I talking about a kid cereal or an adult cereal? Is that it's kids, right? So Reese's Puff, kid cereal. Was it tricks for kids? I was starting to think that cereal that you can't eat if you're an adult. I don't know. So what about if you talk about Fiber One? Well, that's an adult cereal. They're no fun. So we're going to take this data right here and think about the amount of sugar. I'm sorry, Dalen. We're going to talk about the amount of sugar we have found in these cereals. We're literally opening them up, pouring a bowl, and figuring out how much sugar is in that bowl. So we're going to copy to clipboard and hit Control-C. Now make sure you've copied this and make sure to note there's column names at the top of this. By noting there's column names, when you go into Jump, you want to make sure you'll go to File, New, Data Table, File, New, Data Table, and with File, New Data Table, make sure since you said there's column names, you're going to go to Edit, Paste with Column Names. Edit, Paste with Column Names. If you don't paste with column names, you'll get the following problem where it's red because it put the column name in the first column and it thought it was categorical data because it can't make numbers into quantities. Paste with column names right there. Michael, 100 points. Great work. So make sure you paste with column names, kind of restart the process if you didn't do it. You want to make sure it's blue right here. Next, we got to do something a little bit weird. We got to go here to tables and we got to go to stack. So I'll pause on this screen, table stack. We're basically going to take the two columns and stack them on top of each other. So table stack, double click. And once we do this right here, it's going to stack it on top of it. And let's click OK. So now you'll notice we have a label for the cereal label. It did that by default, but it works. And then we have the data, which is the amount of sugar we collected. From here, we have our data properly organized. Make sure this is red, make sure this is blue, restart the process, and make sure to paste with column names if it doesn't look this way. Here we can go to Analyze Fit Y by X. Analyze Fit Y by X is going to be where we look at a Y variable of interest and an X variable to try to explain it. So here, we're going to click the label of the cereal, which might explain the explanatory variable, why there's so much sugar in the cereal. And once we do this, we have our output. Look at this right here. We have the children's cereal, which has tons of amazing sugar in it. We have the adult cereal, which is just no fun, no sugar. This cereal, especially down here, which has like nothing in it, no sugar. It's just paper shredded. I don't know what it is. Let's go here and go to the red arrow and go to t-test. That is the red arrow right there in t-test for the 2-sample t. I know it doesn't say 2-sample, but it is the 2-sample because we have 2 samples. 2-sample t literally means you have a sample of one group and a sample of another group, and the t means you're comparing the means. Remember, Mr. T is mean. You're doing drugs. Super nice guy otherwise. And we're going to go here to t-test. So take a look at the t-test, and we've got the results. Now, if you notice, this is what we saw as a difference. You can literally tell the difference is a unit of about 30. If you think about how far the middles of those distributions are away, this is maybe about 45, and that's about 15, just a guesstimate, because the difference is 36. My guesstimate wasn't perfect, but there's a pretty big difference. And the difference right there is 36 units, 36.4 grams of sugar difference. But that's just what we saw in our sample. That's the difference between the sample means. Now, if you divide 36 by 2, you basically get 18. That is the t statistic, sometimes blanked out on the test. Teaching to the test moments. Sometimes remove that number, you got to find it. We do have the interval down here to estimate the true difference. Like, well, you know, we just took a sample, but what is the real difference among cereals with adults and children's cereals where we're trying to understand what's the real difference between how much sugar they have in them? Well, it's probably between about 32 to 40.5, 8. And that's probably what the true difference is, somewhere contained in that interval. We don't know what the real difference is. We can only estimate it with this interval. And the true difference is probably somewhere contained in that interval. So I am 95% confident the true difference between adult and children's cereals sugar content is somewhere in the interval 42.21 grams of sugar to 40.58 grams of sugar, where adult cereal probably has less sugar than children's cereal, or children's cereal is more than adults. All the numbers are positive, meaning the first mean, notice how this is the first mean right here, is higher. Positive number here indicates first mean is higher. So now that we know how to interpret it, we have all the answers. The answers are right on the screen. So I'm going to bring this over here so I can write it in while doing it, so I can look at it. I'll bring it back so you can see it here in a second. But the lower bound of the interval is the lower, and the upper bound of the interval is the upper confidence limit. And we just need to put in here the same information, but it's that children's cereal probably has more by this amount. Double check your numbers. We're specifically speaking about these numbers with the lower to the upper, to the lower to the upper there also. 4.58, 40.58, 32.2. Good stuff. Check answers. Good to go. That's got it. I thought, and Jonathan has another question. Could you help me with interpreting the true proportion of my diabetic diabetes sample. Yeah, let's do some true proportion interpretations for the project. Heading back to the main screen. I gotta check in on a tweet later. I tweeted to a celebrity and invited them to Stat 201. I've tweeted to them twice now. That's my limit. I love. Yeah, Maria, that's so awesome. Maybe we'll see a celebrity on Stat 201. So if he's watching right now, you're always invited. Any celebrity's invited, as long as they're positive. I don't know. There's probably a few celebrities who'd say, nah, not invited. If you want to come here and have a good, positive time, you're invited to Stat 201. You got a friend. If you're a friend with Tom Cruise, you can say, hey, Tom Cruise, you can come on here. Who's Tom Cruise? Well, I don't think random Tom Cruise. Owner of Suddenlink. Suddenlink, the owner. Well, actually, you know what? Dalen, have you noticed that we've actually been doing pretty well lately? We're going to do some proportion interpretation in a second. There was a thing, like, it was the default IP on the router or something. I changed it, and, like, I don't know if I fixed it or if Suddenlink stopped hating me, but it's been really good. We haven't had any lag. Mubot's gonna freak out right there in a second. Say lag. My brother should see all the craziness and nonsense. We need more keywords for Mubot to react to. We got to keep thinking of these things. Stat 201 project proportions. So true proportions. So yeah. Okay, so let's go talk about the project. And is the timestamp accurate? It is. Here we go to the project. So we're going to do a little project talk right here and talk about true proportions and all that good stuff. Let me get the project going on the screen right here. The Stat 201 project, dealing with proportions, coming up here in just a second. So in the project, we're going to look at all the proportion stuff. Here we go, instructions. One sample Z right there. We need to make sure we have a categorical, talking about a famous. Oh, that's interesting. He's still around, right? Hope he is. But I'm just saying a hard time applying to this example. Well, so whatever we're looking at here. So which specific part of this are you wondering about? The hypothesized proportion or so when we interpret our interval, like interpreting intervals and stuff, if we go over to data, we could actually run watch this. This would be, yeah. Watch this. Analyze distribution. And what are we trying to understand? Well, that's boring. That's boring. So let's. Well, that's awesome. Yeah, I think I heard he was in Knoxville at one point. Okay. Yeah, maybe I heard about that. Analyze distribution. We want to know. We go to the grocery store and we take a sample of 40 random cereals. Does that make sense? Who's following me with this example right here? I went to the grocery store and I bought 40 random cereals. And then I looked and asked, are these cereals what's or what's? I went to the grocery store and bought 40 random cereals. I just did it while we were talking right here. I just ran out the door. I was like, what? And then I'm like, I'm back. And I got 40 random cereals, right? But I want to investigate what about these cereals. What is my variable of interest about these cereals? Oh, that's cool. Let me check that out, Dylan. What do I want to understand about these cereals? What is my variable of interest that I'm interested? The Y variable, the question. Is it adults or children cereals? Great job, John, right there. It's like, is this an adult cereal or children? I know it's a little bit subjective, but when we see Fruit Loops with berries and marshmallows, we're thinking children's cereal. I mean, I'm going to buy it anyways, but when we see Fiber One, now with more fiber, we think adult cereal. Don't want that. So with this right here, we have asked, is it a children or adult cereal? Now, we bought 40 random cereals from this store. They probably have more. We're considering this is like a huge chain with all, this is H-E-B. They're all over Texas. So we're saying, when you think about it, H-E-B, if you walk into it, the cereals in H-E-B, are they more adult or more children's cereal? Now, we did see in our sample more adult cereals. So someone might say, well, obviously, there's more adult cereals at H-E-B. But I only bought 40 random cereals from H-E-B. And we'll consider that a random sample of all H-E-Bs to understand what HEB carries in their stores, which would be tons of different cereals across things. So we're assuming this is less than 10% is what I'm trying to say. Not the biggest worry or assumption on most questions. When we do this right here, we can go right here to something called a confidence interval. I'm going to make a 99% confidence interval. I'm making 90% instead today. I'm going to make a 90%. That's a button right there. We'll zoom in a little bit here so you can see it a little bit better where I'm clicking. Click here on the button for confidence interval and go to 90% or whichever you choose. You can put in wacky levels by going to other and do weird confidence levels. Most statisticians are going to use like 95. That's the default. 90 is also common-esque. Also 99, but 95 is your classical 0.05 alpha on the two-tailed test. So we go here to a 90% confidence interval, and it's pretty much on the screen. I guess we could keep it over here. Now, when you look at this, what are we thinking? We want to know for all HEBs, that exist, we want to know the what. Because we're an adult. We're not a kid. We want to know the what. What do we want to investigate? We are interested in the what. This is my project now, looking at cereals. I want to understand the what of what. So try to finish the sentence. Brian wants to understand the true, some P word, of this at HEBs. Brian wants to understand the what. So what does this output then tell us, and what does it mean? So we saw 22 out of 40. That's what that stands for. 22 out of 40 were adult cereals. That's 55% of our sample. The true proportion, right? Brian wants to understand the true proportion of what's at HEB. Keep going, Michael. Great work right there, Michael. Brian wants to understand the true proportion of adult something at HEB. Not going to eat that. Lucky Charms. No, I'll go eat it anyways. Brian wants to understand the true proportion of what? Kind of, and so pretty much, Jonathan, that's where we're going with this. I want to understand the true proportion of adult cereals at HEBs. Does that make sense? Like, if you were to walk into an HEB at any time, it's not that there's 55%. That's a guess. Like, it's probably about 55%, maybe. But we need some sort of interval to say, well, we guess it's about 55, but it's probably somewhere within this interval. So I am 90% confident, I'm somewhat confident, that the true proportion of adult cereal at HEB is contained in the interval 42 to 67. I kind of rounded a little bit there. Does that make sense? I am 90% confident that the true proportion of adult cereal at HEB is contained in the interval 42% to 67%. Now, what if someone said to me, you know what? I think from my beliefs that adult cereal is like 2 out of 3 cereals is adult. So they say, I think 2 out of 3. This is a hypothesized proportion, as in they have a P0, and their P0, which is their hypothesized proportion, P0, is equal to this right here. So they think, I think it's about 2/3 of the cereals at HEB, from my experiences, are adult cereals. Would you say, or would you say, maybe, possibly, maybe, that seems possible. What's your thoughts on that for a person who believes that? That's their hypothesized proportion that they believe currently. Would you say, that is preposterous? You do jest. Or would you say, yeah, sure. Yeah, sure. What's your thoughts? How would you use this interval then to talk over that idea with them? Because you say, I am 90% confident the true proportion of cereals at HEB that are adult is about 42 to 67%. So look at your interval. They have given you a value what? They have hypothesized a value. What? They have hypothesized a value that 0.66 is a value that is where? Is it here? Yeah, it seems possible. It's like, sure. And remember, that is their hypothesized value. It's contained within your interval. So would you reject that value or not reject it? Exactly, Michael. Good practice, Michael, right there. Yeah, it's possible. It's within my interval. I'd be like, yeah, it seems possible. So would you say I reject that value, or I don't reject it? What would you say? Not reject. I can't reject it. Now, what would be the associated, and look how the math is done. This is the confidence level. So can you deduce the alpha level? You can actually see it right here. Think about the math that was done to achieve this confidence level. This is the level of confidence we used. So deduce the alpha level right here. What alpha level would you not reject it at? So you see it's kind of hinting at it by saying 1 minus alpha is this. So what was the alpha level done on the two-tailed test that you did not reject that value on? 0.1 right there. And do you see how it works? It's just 1 minus alpha's confidence level. And that's for the two-tailed test. So remember, confidence intervals look like this. Two-tailed tests look like this. What about your other friend who comes along and says, I think like 90% of the cereals at HEB are adult? And you're like, you think 90% are adult? And they're like, yeah. And I'm like, you're crazy, man. You're crazy. Watch this. You think 90% is adult? Let's test that. 90%. Really? 90%. I don't even need to run this test. I don't even need to do this. Because if you're asking me to test 90%, then that's not even in my interval. I'm not talking about that 90%. So to not add confusion, they say 80%. I don't want you to think I'm talking about that 90%. We're saying they hypothesize. You don't need to do this. This is not part of the project. I'm just showing how to do it if you actually wanted to do it. They hypothesize that 80% are adult cereals and 20% are children's cereals. Those are not contained in the interval. So when I run this test right here, the p-value will be high or low. So the values they're giving to you are ones that you would reject. So when I run this test, which is not part of the project, it's what the project is showing you can do at the interval. These p-values will be high or low. Hint, I can reject them. I'm like, yeah, I don't think those your values you're hypothesizing, the values you think are true. We're gonna have a low p-value. We're gonna reject the null, and boom, look at that. You just figured out that's low p-value. Reject the null because those values are not contained in the interval. I don't think they're true. So low p-value means this is not likely. What I saw in my data was not likely. Sports reporter, we could do that. We'll finish off with that. Is this making sense here, Jonathan? Tell me what you're wondering about. We're going to end off here with sports reporter because we have class in 20 minutes. Heading back to the main screen. I think the soda's kicked in. Maybe celebrity will show up. Last thing I want is for people to like, I don't know. Like, what if people are like, yes, like started like tweeting at him? I don't know. Some celebrities are like, why not? Let's just do it. Awesome, Jonathan. You're welcome. I just want, when you look back on your life, you want it to be interesting. You want there to be fun and craziness. Yeah, I don't think he's replied at all. It just flew over the radar. We'll see if he sees it. New Doctor Strange tonight. Is he a part of that? What is that? Let me see one thing. What is this? Strange New Worlds. Oh, no wonder. Was it a new... Interesting. Okay. Well. Let's do the last question here of the day. We're doing the sports reporter. This is a notation question. Notation. Gotta know our notation. Here we are with the sports reporter. Let's do it. Here we go. So on this question right here, it's all about your notations. So take a moment, Statue 1, Chapter 17, Sports Reporter, and notice that they give you the notation. So what you're going to do here is you're going to solve it. Now, sometimes our test questions rather have you solve and identify things, especially in jump output. You'll notice in a lot of the questions, I will bring up things like the jump output and talk through what this output means because there's a lot of test questions that show the output and we need to know what it means. So check out Canvas content and other things where we go through the jump output and solve it. So with this right here, let's take a look. We're going to take this data right here and bring it over. Now, what they're wondering is, if I remember this question quite well, they're wondering if baseball players are older than football players. So which way would the null go? Well, the null hypothesis always has the what sign. We have baseball minus football. There's a difference right here. The null always has the what sign, though. So we assume that the difference is what? The null always has this sign, so we're looking at the difference between the means. Because when we call the two sample t, we have two samples. That's the t part of it. Great job, Maria. The null has the equal sign. And we have our two samples. That's the two of the two sample. And then this is the t of it. There's the two sample t. The two sample t is looking at the quantitative difference between two means. And the null has the equal sign. And then we are wondering if baseball players are older than football players. Now, it's a little confusing when you write this, but you can remember it this way. Whatever sign you put right there could also be put in right here. Just mathematically, the way it works, you could rewrite it as this, that baseball players are on average older than football players. That's the way the question goes. It wonders if baseball players are on average older than football players, and that is the alternative hypothesis right here. So, null hypothesis, alternative hypothesis. And there we go. So now that we have the null and alternative written, we need to actually test the difference. To test the difference, we need to take the two sample means, 27.7 minus 26.8. This is what we found when we talked to football players and baseball players and found the average age for them. So there's the average of baseball and football respectively. Divide by 3.96 squared over 31. And I should write this out for you. The formula, give me a second because usually I write the formula first. Y bar 1 minus y bar 2 over there we go. And that's got it. So the formula is it always, nope. It could be lower minus higher. Then the difference would be negative. There's problems we did earlier where the difference was negative. I think so this was a negative difference right here. This was a negative t statistic. Just the way it was written, you see sample mean 1 minus sample mean 2. Then the t statistic is negative. Does that make sense? In this instance, we got a negative t statistic. The way they set it up, it just depends. This was small glass minus large glass. The way they write this problem right here is they say, let the mean of professional baseball players be mu1. So it's the first mean is baseball player 27.7. Usually it goes in the order, the bike route question goes in reverse order. So that is confusing when you get to the bike route question. Right now we're computing the t statistic. So we just need to solve that equation. Solve that equation. 3.96 squared divided by 31. Square root. There we go. 0.968. That's going to be a t statistic of a little less than 1. And so this is the t statistic right here with degrees of freedom. Do they tell us? They might tell us that. No, I don't think they do for this one. We'll need to find those degrees of freedom in a second. That's not the t. That's just the standard error. We need to take that difference and divide it by it. So 27.7. And there it is right there. 0.847. There we go. And so that is the t statistic. And now we have to find the degrees of freedom for it. The degrees of freedom is found by using a degrees of freedom calculator. Reason being, we have a saying about this. The two sample t has degrees of freedom that are what? Say it with me. The two sample t. What's the formula? Does anyone know the formula? We got to remember it. How do we remember this formula? The two sample t has degrees of freedom that are what? Yes. That sounds like a does not equals correct. If they're testing to see if they're equals, the alternative would be not equals. And the two sample t has degrees of freedom that are too complicated. We don't solve this. We use the applet right here to solve it, and we input the numbers on the screen, 31, 33. Those are the sample sizes, and then we input the standard deviations, 3.96. And make sure they go respectively with their N1, S1, respectively, 2.73. There we go, all there. And 52.8849. Now we have to go over here and go to a t-applet. So now we go to the t-applet and we put in the degrees of freedom because the degrees of freedom tell us which shape of t we're using. There's infinite t's, but they're all decided on by the degrees of freedom, tell you how it looked. Less degrees of freedom, Mr. T has smashed it down more. More degrees of freedom, more free to be normal. And this one's kind of normal. Not too normal, but kind of. We are doing the greater than test. This is going to be a p-value about 0.18, I believe. Close to 0.18, something 16 to 20%. Yeah, about. More like 20%. There it is. Is it exactly 20%? Oh my gosh, it's exactly 20%. I should have just put that in as a guess. This is the right-tailed test, the greater than test, and we are graphing above a t-score of 0.847. 20% of the curve has been shaded. So now that we have this, we can go over here to the t-statistic, round to 2 decimals. All those decimals gone to waste. The p-value here round to 3 decimals, but it's that, basically, 20%. And the p-value is way above the alpha. The alpha right here is the rejection criteria. Our p-value is way above, so we fail to reject. There is not evidence for the alternative. And that should do it right there. Oh my gosh, wait, we're trying to submit the quiz. We don't want to do that. 50%, what did we do wrong? I think we did some math wrong. Uh-oh. This is what happens when you go too quickly. It looks like we did the math wrong on this because that would lead to a wrong t value and a wrong p value. So let's try again. Oh, did I not square root the bottom? Yep, that was wrong. Okay. No. There we go. 9 point. There it is. Wrong math. Which equation? Yeah, should be right. It's gonna be a smaller p-value. Something like that. It's gonna be smaller p-value now because we're further over on the curve. Where's our curve with this? Go 17.1. Close with my guess right there. I'd probably be right. There we go. So there was a math error right there. The big thing is putting in the numbers. So when we plug in numbers, we have y bar 1 minus y bar 2. There's the y bars. Sample size, or standard deviation 1, standard deviation 2. Sample size 1, sample 2. Like which graph from, and then when... So right here, these are all, for this problem, this is group 1, and this is group 2. So this 31 here is N1. Does that make sense? Notice how this is group 1, and so everything right here is group 1. And everything over here is group 2. So that's group 1, group 2. And so it kind of lines up respectively. Just be careful, the S's go on top. Yep. So you just have mean 1 minus mean 2. No worries. It's like once you see it, you're like, oh, I see it now. It's like, it's one of those things once you see it, it's like, yeah, and I made a math error on it, apparently. I'd have to look over in the video where I did it, but I didn't, maybe I didn't square the 2.73 or something, but there was an error. Well, I'll be, so sorry, everyone. Every once in a while I make an error. That was a math error today, and I also did a rounding error today, so we had a rounding and a math error all in office hours. It happens. Double check your work. We always got to double check. With that, we'll be back. Time for class in 10 minutes. Wow! Bye for now, everyone. Bye! Jimmy's, I'll look over the screenshot here after class, Dylan. Good work. Excellent work. I will take a look. 500 points. Class coming up soon.